guys? Today we're going to look at exponential functions. Now, as you can see, an exponential function is a function where the base is the constant and the exponent is the independent variable. So it's kind of the inverse relationship of our polynomial functions, where we may have had x to the second power. Now we're going to have something like 2 to the x power. We're just swapping that relationship. So our base is now our constant. Our variable is now the x, or the independent variable. A couple restrictions on exponential functions. The base will always be positive, so it's always got to be greater than 0, and it'll never be 1. The 1 part just kind of makes sense because if that's a 1, you're just going to get a horizontal line at 1 because 1 to every single power is going to be 1, so it doesn't really do anything for us. So we want to look at kind of that 1 is our barrier, because we have something special that goes on when we're between 0 and 1, when we have those fractional values, and when we're greater than 1. So get some special relationships in those two circumstances, and we'll look at those in a few minutes. But first, let's kind of look at what's going on graphically in an exponential function. So let's say we have this function here, f of x equals 2 to the x power. Well, let's fill out the table and see what is going on, what kind of points we produce. So I've got all these different values for x, and let's just plug them in and see what we get. Well, 2, if I take negative 2, plug it in, 2 to the negative 2. Remember, negative exponent means multiplicative inverse. So it's not 2 to the negative 2, it's 1/2 to the positive 2. So 1/2 squared we know is 1/4. 2 to the negative 1 would be 1/2 to the positive 1, which is 1/2. 2 to the 0, anything to the 0 power is 1 except for 0. 2 to the 1 gives us 2, 2 to the 2 gives us 4, 2 to the 3 gives us 8. So we kind of see we get a little different relationship than what we had with the polynomials. We're multiplying each of those by 2. So if we plot, we should get obviously a very different type of graph than we did from our polynomials. So let's plot the points. Negative 2 and 1/4. So we'll say we're about right there. Negative 1 and 1/2. It's about right there. 0 and 1. 1 and 2. 2 and 4. Oh, let's go to 2. 2 and 4, and 3 and 8. Oh, that's a little difficult to do sideways, but as we connect that, we can see that we'll get that. Sorry about that. You can see we get that relationship right there. So this is the graph that we've produced from our exponential. So it's very similar in that it's going to curve like our exponentials did, but as we can see, instead of it turning around at a vertex, it actually seems to flatten out. Well, let's look at what's going on. As I move to the right, I'm just doubling my numbers. They're getting twice as big every single time. 4 would be at 16, 5 would be at 32, 6 would be at 64, and so on. As I go to the left, my numbers are getting half as small. We're cutting them in half. So we're at a half, a fourth, we'd then be at an 1/8, a 16th, a 32nd, a 64th, a 1/128th, and so on. So the numbers are getting smaller and smaller and smaller and smaller. Well, what's happening here is if the numbers are getting smaller and smaller and smaller, what's the smallest that they can get? Can they ever make it to 0? Well, the answer is no, they can't, because you can't cut something in half and eventually make it nothing. There's always going to be half of the previous amount left. Even if it's microscopically small, there's still going to be half of what was originally there. So we're always left with some value. So what we get at 0 is an imaginary line that we call a horizontal asymptote. And what a horizontal asymptote is, or an oblique asymptote also, is a line that we tend to approach and level off at as we get towards either positive or negative infinity. And we'll focus on those a lot more when we get into our unit on rational functions. But this is kind of our first little taste of horizontal asymptote. So it's a line that we're going to get really close to. In some cases, we can cross that line and then level off at and then come back to it. But in the case of exponential functions, we're going to get very close to it and never actually get to it, but we're going to tend towards it. We're going to approach 0 in this case, but never actually get to 0. So a very important concept and terminology you need to familiarize yourself with. Now let's talk about what the domain and range of an exponential function are going to look like. Well, domain we know is what we're allowed to put in. What can I put into my function that actually produces a graphable value, a real number? Well, if I put in positive numbers, do I get real numbers out? Well, yeah, I put any positive number in, I'm going to get some really big number, in this specific case of 2 to the x power. If I put in a negative number, I'm going to get some, infinitely small, as I approach towards a negative infinity. I'm going to get some very small number out of that. So it seems that no matter what I put into my function, I'm going to get a graphable, a real number out. There's nothing that kind of breaks math law like we had with square roots of negative numbers. It just said, no, this is not a real answer. We can't function here. There's nothing we can do with it. So no matter what number I plug in, I get a real graphable number out. So we can say the domain is all real numbers, or negative infinity to positive infinity. So every number from negative infinity to positive infinity will produce a graphable value inside of our rational or our exponential functions. Now the range is a little bit different. Range, remember what we did with our quadratics, last time we really talked about range, was from that minimum point up or from the maximum down. Well, it's very similar to that in that we have this horizontal asymptote. We have this value that we're going to level off. It's not going to keep going towards negative infinity on the y-axis. It's going to level off at some point because the numbers are getting smaller, so that they're going to flatten out. That's going to give you your range. That's going to give you that minimum, or as we get into transformations, maximum if we were to do a vertical reflection on this problem. But so the range is really from that horizontal asymptote, that's our minimum, on up. So in this specific case, we can say the range is from 0 on up. Now again, remember our notation, our interval notation, we can't ever actually equal 0, so that's why we don't put the bracket on 0. It's all values greater than 0. And again, if we had a transformation, a translation or a rotation reflection, that would obviously impact that range. But just generally speaking, that's what the range for a very basic f of x equals b to the x exponential function is going to look like from domain and range, from a domain and range standpoint. Next, let's take a look at how do we determine if a relation, if a group of points actually is exponential or not. As you can see here, I've got this relation of -3 to 54, -2 to 18, and -1 to 6. And we want to determine, is it exponential? And if it is, we're going to write an exponential model for it. Well, what does exponential mean? Well, think back to what polynomials were. Polynomials said we're multiplying by x every time, right? It was x to the second power, so we're going to multiply by the same value twice. Or we're going to multiply by the same value 3 times in terms of a cubit. So it was multiplying. Well, multiplying showed up in relations as that finite difference, right? You're adding the same amount again and again and again because that's all multiplying is. Well, exponentiation is going to show up as multiplication because you're multiplying by the same number each time. So that's what we're going to look for. Instead of looking for finite differences, saying that we add the same from each term to the next, we're going to say we're looking for finite ratio. Okay, so it's not a finite difference anymore. We want to see a finite ratio. So it's what am I multiplying to transition from one domain value to the next. So we're still constant here. We still increase by 1, increase by 1. So we have a constant increase there. Is the ratio of the y's consistent also? So for you say, how do we get from 54 to 18 and from 18 to 6? If you don't recognize that it's divide by 3, ratio implies division. So we just set it up. 6 divided by 18 is 1/3. We're multiplying 18 by 1/3 to get the 6. Same thing here. 18 divided by 54 is 1/3. We are multiplying 54 by 1/3 to get 18. We always want to think of it as a multiplication problem, not a division problem. That's going to help us out a lot when we get to our geometric sequences and series later on in the course. But for now, we really want to think of it because that's what exponentiation is, multiplying by the same value every single time. So in this, we recognize we have this finite, this constant ratio that says we're multiplying by the same amount. 54 times 1/3 is 18. 18 times 1/3 is 6. So yes, it is exponential. Sometimes we call those a common ratio also, which is, again, that's a sequence and series term that we're going to explore later on. So since it is exponential, we want to write this exponential model form. F of x equals ab to the x, which we should recognize. B to the x was just the parent function we were discussing a minute ago. What's the a going to do to that parent function? When I multiply value times a parent function, we should remember from our transformations that that's just going to perform some type of vertical, horizontal or vertical stretch. Sorry, vertical stretch or compression. Vertical stretch or compression. And if A happened to be negative, then we would get a vertical reflection with that, but that's, you know, something for another day. A in these is going to be positive because that's kind of where we're at when we're working with exponential functions. So let's create this model for it. Well, let's take it out of f of x and think in terms of what we have here, x's and y's. Or we can leave it x's and f of x because it's what we have it labeled here. So if I have f of x equals ab to the x, how many things do we not know in this function? Well, I don't know a and I don't know b. That's two unknowns. So to figure out two unknowns, then I'm going to need how many equations? Two equations. So it's just like we did with our quadratics. In quadratics, it was ax squared plus bx plus c. There were three unknowns. So we used 3 points to set up three equations. Well, here we just have the two unknowns. We have b, which we call the growth factor, and we have a, which is our vertical stretch, or stretch factor or compression factor. And we're going to then figure out what they are by taking 2 points for our two unknowns. So you pick any 2 points you want out of there. I like the nice, smaller, cleaner numbers. So I'm going to use -2 and 18 and -1 and 6. There's my x's, there's my f of x's, x and f of x. So if we just substitute those in, f of x is 18 equals ab to the x is -2. Here we have f of x is 6, ab to the -1, and what do we have here? System of equations. That's all it is. So this one I would probably recommend doing substitution on instead of linear combination, just because it's the way that works best in these. So if we look, a is easy, is in both of them, a to the first power. So if we isolate a, should be pretty easy to do. So couple ways you can do this. If you're really good with your exponents and you understand really what's going on with your exponent combinations, I can recognize it as if I want to get rid of a -2, I need to multiply it by a +2. -2 plus 2 should cancel out. If you don't recognize that, you can just take a step real quick and change it into reciprocal. That's what negative exponent means. It implies multiplicative reciprocal. And then how do we get a by itself? Times b squared times b squared times b to the first times b to the first. So we have a equals 18b squared and a equals 6b. Same thing as if I'd have recognized up here to get rid of a -2, I multiply by a +2. Still would have put me here. Substitution says once they're equal to the same thing, we set them equal to each other. 18b squared equals 6b. And now we have a quadratic equation. How do we solve a quadratic equation with multiple degree x's or multiple degree variables? We've got to solve it by factoring. Get them on the same side, factor out the 6b that's in common, leaves you 3b minus 1. Set each factor equal to 0. 6b equals 0, 3b minus 1 equals 0, so b equals 0, and b equals 1/3. Well, we recognize that you can't have a base of 0. Remember, that was our two rules for the base. One, it has to be greater than 0, and the other one, it cannot be 1. So it can't equal 0 or a negative number, and it can't equal 1. So we go with the other solution, b is equal to 1/3, which we remember showed up right there. That was how much we were growing by, or in this case, shrinking by 1/3 every single time. So if I recognize it here, I can just go straight to using my b and then solve for my a's. If I don't, this technique will get me there. So b is 1/3, we're good there, and then we just finish out. So we have f of x. Let's check that again. Not to that point yet. Going back to the very beginning, just doing our substitution. 6 equals a times 1/3 to the negative 1, right? 1/3 to negative 1 means multiplicative reciprocal, so that's a times 3, and then how do we get 3 by itself, or a by itself, divide by 3, a equals 2. So now we put it all back together. F of x equals a is 2, b is the third, raised to the x power. So that's how we take 2 points and turn them into an exponential model after we've recognized that they are indeed exponential. So that's all it takes to create an exponential model is 2 points. So it's just a quick little substitution technique. Yes, you could use the regression function of your calculator. You just do exponential regression and it would give you the same look there. And we could create a more complex model if we wanted to. So we wanted something with horizontal shifts, put x plus h up there. Vertical shifts, put a plus k, or sorry, x minus h up there, and put a plus k on there. We can create a more complex model. You would just need more points to get substituted in for your f of x and your x to then go through and solve your system. So that's all just depending on what scenario you're presented with. This is what we're going to focus on in this course, in this Algebra 2 course right now. So, exponential, yes, because they all multiplied by the same value, and then that's the model. What's very interesting is if we'd have carried this process out right here, if I'd have gone another one more would have put me at 0, and then I'd do times 1/3 again. Well, what's 6 times 1/3? A third of 6 is 2. So what we can see is 2 is what's happening at 0, and then 1/3 is our growth, or our decay factor is what we would call it in this case. And we'll talk a little more about that here in a second. But what you should always recognize, because what's 1/3 to the 0 power? That's 1. 2 times 1. Your vertical stretch, because remember the parent function is going to be at 1. B to the 0, it doesn't matter what B is, anything to the 0 is 1. So your parent function is always going to have a y-intercept of 1. That vertical stretch or compress is what's going to impact it. So if I've got this right here, I don't even have to go through all this because I know what my growth or my decay factor, my B is in this case, because it's that finite ratio, and I know where I'm starting at. I know I'm vertically stretched by a factor of 2. So this is your A. Another way you can get your A, and then this is your B. Another way you can get your B. If it's presented in that form. A lot of times they're just giving you 2 points and you've got to go from there. So it kind of gives you 2 different techniques to be able to attack that relatively simple exponential model. Now I've used the terms growth and decay multiple times, and it comes from this idea of the values as I tend towards positive infinity increasing or decreasing. Well, we saw with the first example we had that 2 to the x, that our graph was getting bigger and bigger and bigger. We had something that looks like this, with our horizontal asymptote. This obviously shows exponential growth. As we approached positive infinity, as our x's approached positive infinity, our y's approached positive infinity. We're growing exponentially. And that was for the f of x equals 2 to the x. Well, this next example we had, well, what was happening? We were at 54, 18, 6, then 2, then we're going to be at what? A third of that, 2/3, and so on. So, that's horrible, but you get the idea. This would be the graph of an exponential decay. The function is getting smaller and smaller and smaller as we approach positive infinity. And that was our f of x equals 2 times 1/3 to the x. So they both had a 2 in them. What is different about them that is causing the function to actually grow or decay? Well, that thing that's causing it to grow or decay is right here. This is our growth factor, or our decay factor. So, can we generalize it? What does the base have to be to make this function grow, to make it get bigger and bigger and bigger and bigger? Well, for it to get bigger and bigger, all it's got to do is be bigger than 1, right? I'm multiplying it by 2, or I'm making it 3 times as bigger, or 4 times bigger, or 1.5 times as bigger, or 1.01 times bigger. So it's getting bigger because it's bigger than 1. It's the 100% it was before. To create a very generic model, it starts out at 100% of what it is, and it's increasing by some amount. It's increasing, so it's bigger than 1. So we say it's exponential growth. It's the growth factor to the x. Okay. Now, when it's a decay, when it's smaller than 1, it's not negative, because remember we said that our base can't be negative for us to really classify this as an exponential function. It's a different beast that we try to tackle when we have a negative base. We said that our domain has to be what? Greater than 0 and not equal to 1. Well, if we're saying everything that's greater than 1 for our base, all the bases greater than 1 make it grow, it's got to be all the stuff smaller than 1 that makes it shrink, makes it decay. And that makes sense, right? If I have 3/4, I'm 3/4 of what I was before, right? We're multiplying by 3/4, 3/4, 3/4. So it's getting a 3/4. It's 25% smaller in that case. So it's shrinking every single time, or a half, or a third the size it was before. So we would say that if b is between 0 and 1, then we're decaying. We have exponential decay, and that would be our decay factor. So in this very, very generic exponential model that you really need to be familiar with, and it'll come up a lot in when we start looking at some applications of these, is if we are adding something, say we're increasing by 10% per year, that's 110% bigger than what it was the year before. Okay? If I said it's 10% less per year, then it's 90% of what it was the year before. So we get this very, very generic model that we need to be familiar with. And it'll be typically written like this. And the reason we write it like this is because this R is called our growth rate. Okay? Our rate of increase or rate of decrease. Okay? Not growth factor. The whole thing's the factor because it's what we're multiplying by. This is the rate of increase or rate of decrease. A, as we saw a few minutes ago, that's your initial amount. right? That's what's going on. We'll try to spell amount correctly. That's what's going on when we're at t equals 0 or x equals 0. That's your y-intercept. And this is your amount at a specific time. And this is your length of time. So we use this a lot. And your units will be the same. We'll work on ways to kind of normalize these units. But we use this to really explain a lot of things like compound interest or half-life, or really anything that does with multiplying the same value again and again and again. Think of half-life. Half-life, I'm taking this value and saying it's cut in half every so many years or so many seconds or so many minutes or whatever we happen to be talking about. So it's getting cut in half again and again and again. So that's an exponential decay type of thing. Or if I'm talking about compound interest, I get 8% more per year, whatever we happen to decide the percentage and the interval is. So it's growing by 8%. So you're 108% of what you were the year before, and so on. So we'll focus on that model a lot more later on, along with a few other models, but they're really based off this idea of we're either going to be adding or subtracting from 1, right? We're either greater than 1 or less than 1 in order to get this exponential growth or decay. Now, there's a very special number that I want to talk to y'all about, just to kind of introduce it. And it's a number called the natural base. And we will look more in depth about where it comes from, but it is an extension of this model right here. It's the natural base, and we just use it, we represent it with E. Okay? So anytime you see a formula or a reference to E, just think of it like pi. It's a constant. It's a number that shows up a lot of times in nature, and we do a lot of things with it. And like I said, we will look more in detail when we're exploring this function or this specific model a lot more closely about how we actually create this E. Got to put in a little more stuff before we can really get into it. But the idea is that there's a number that shows up a lot, and it is a constant. It's approximately 2.71828-ish. It keeps going. Like I said, it's irrational like pi, and it's constant like pi, and it never changes. So anytime you see something referred to the natural base, or you see that letter E, it's talking about that number right there. It's a button on your calculator, and we can just go to work with it. So it's a new type of constant that we will work a lot with in this unit as we work with exponential functions. So that's it, exponential functions. We know how to identify growth or decay, right? B is greater than 1, we say it's exponential growth. If B is between 0 and 1, it's exponential decay. We can write an exponential model. We need 2 points to be able to get that exponential model for the a, b to the x model. Domain, negative infinity to positive infinity. Range is everything from that horizontal asymptote up. And for what we're doing right now, that horizontal asymptote is going to be at 0 because we won't get to the transformations until later on. And that's it. Exponential functions. The exponent is now the variable, and the base is now the constant. And I will see you in class tomorrow, guys.